Okay, good morning everyone. Last time we reached the proof of this theorem, which is if you have a function that you know the Laplace transform for it, then if you integrate that function, what will happen to its Laplace transform? It says that if you integrate the function, then it is as dividing its Laplace transform by s. Let me show you the proof. I will call that function g of t, right? And I'm gonna just give you a note here that g prime of t is just the derivative of the integral, right? Yeah, f of t dt, right? And you know from the fundamental theorem of calculus that the derivative will cancel the integral and you get f of t, right? So the first note is g prime of t is just f of t, right? Now what we need to do, I'm gonna apply just, let's go to g prime of t. And if you apply the Laplace transform of this, then using derivative rule for Laplace transform, it says you multiply by s and you take the derivative away and you get Laplace transform of g of t, right? And then minus g at 0. Yeah, this is the definition of the derivative, or not the definition, it is how you do the Laplace transform for the derivative. Then to get rid of the derivative here, I'm cancelling the derivative and multiplying by s and subtracting g of 0, g at 0, right? Now let me write here s Laplace transform of g of t, right? And then g of 0, this g of 0 is the integral from 0 to 0, because g of 0, if you have t here, then you have t here. If you have 0 here, then you have 0 here, then it will be the integral from 0 to 0. F of t dt, right? But if you integrate any function from a to a, then you will get 0, right? Then what I got here, let me rewrite things. What we got here, the first thing is Laplace transform of g of t. So I got here, let me write this, Laplace transform. What is g of t? Here is g of t. I'm putting this back here. It is the integral from 0 to t f of t, yeah, dt, right? And this is multiplied by s, and this is equal Laplace transform of g prime, but I can put here g prime is f of t, right? I can put here f of t, and I get Laplace transform of f of t, right? But then I can replace this back from this thing here. Yeah, from this thing will be f of s, right? This is f of s, and then equal to s times whatever there, right? Now the next step is just dividing by s. If you divide by s, everything by s, this means s times whatever here, right? Times that thing. Now dividing by s, then you will get your result. So you will get the result. So just I'm saying here, if you divide what you get here by s, then you will get what you want. Okay, now we are done with section 7.3. Now I'm going with section 7.4. 7.4 is the Laplace inverse transform. So let me write the title now. Here is the title. The title is Laplace inverse, or the Laplace inverse transform. And I will write for this L minus 1, okay? Now let me tell you the story. What is the story? So in the past, I was giving you f of t and asking you for f of s, right? And so I give you a function of time, I ask you for a function of frequency, and you were using Laplace, right? Now we are changing the thing. I give you f of s now, and I ask you to go back to f of t, and then you do that using Laplace inverse, right? In other words, I will give you a fraction from the column number 2 in the table 7.1, and I ask you to give me the function of time, right? So I give you any of these fractions or something close to them, and I ask you for the function of time. Okay, in other words, if you want it in a different way, I can tell you now in the past. So in the past, this is the output, right? Output, right? Output is f of s, and here is input f of t, right? Now, in our new case, I give you function which is, this was Laplace, right? This is Laplace inverse. It is doing the inverse. The inverse. You have f of s here. This is the input, yeah? And I'm asking you for the output here. Sorry, output. And it is f of t. So it is the inverse of the Laplace transform. This f of t that I'm going to ask you, it will be a continuous function, should be a continuous function, continuous on 0 up to infinity, right? Because you know, when you do the Laplace transform, then you are integrating f of t from 0 to infinity. Okay, let me start solving some questions. This is very easy thing. I will not ask you for doing any integral. It is just comparing with that table which is 7.1. So let me start here by solving questions. Question number 1, determine the Laplace inverse transform for the given function. Now you will ask yourself why we need this. If you go back, so if you go back to our first section, it says I'm going to give you a differential equation. You do Laplace for that, you do some algebra, you do Laplace inverse, and then you get the solution for the differential equation. This is why we need Laplace, and then algebra, then Laplace inverse to get the solution for a differential equation. Now let me start with this question. I will give you the page number for this question. It is page number 396. What is that? It says I have f of s equal 6 over s minus 1 power 4. So all the questions that I'm gonna ask you, it will be a fraction, because anything here is a fraction. But it is not necessary, will be very easy function from there. You need to do some adjustment on your fraction to be able to guess the f of t. Now let me compare here which one is the closest one. It seems to me that you have here always we start, so let me go here. Always I will start looking at denominator, starting with denominator always. Yeah, so I have s minus a number and I have a power here, power 4, right? So I have s minus a number and I have a power here. So it seems to me that I will compare this with this function, line 1, 2, 3, 4, 5, 6, line 6 in the table. Now comparing, as I said here, always start with the denominator, then you need to compare here solution. So comparing, so from table 7.1, column 2. So you start with column 2 and you go back to column 1, then s minus 1 power 4, yeah, should equal to s minus a power n plus 1, right? And from this I can look here and compare. It's clear that a should be 1 and n plus 1 should be 4, and if you solve for n equals 3, right? If you get n and you get a, let me see, is that enough? Okay, let's go here. So this is what you're gonna get. What is missing? N is missing, a is missing, but t is the variable. You cannot replace t. You need to replace a and replace n. For this reason, our Laplace inverse of that function, which is 6 over s minus 1 power 4, will be, let me write this. Okay, just a minute, before doing this. So denominator is okay, denominator is okay. Now let me look at the numerator here, numerator. So it says when you get n, check the numerator. So is n, so let me here, checking the numerator. Now I have n here, yeah. Let me checking the numerator. N factorial is 3 factorial, which is 3 times 2 times 1, right? And I'm getting 6. Is that the numerator? Yeah? Is it the numerator here? 6? Yes. If it is yes, then you are done. Then the Laplace inverse of your function, which is 6 over s minus 1 power 4, should be e power a. What is a? It is 1t, and then here t power n, which is 3. So you are done. So the Laplace inverse for this function is e power t times t power 3, and of course t will be greater than 0, right? Let me solve another question. Always the question will be the same. We are looking for the Laplace inverse for a given frequency function. Now I'm going to question number 2. Here is question number 2. And what is the question? The question is saying the following. So you have 6 over s squared plus 25. 6 over s squared plus 25. This is your f of s. Yeah? Now solution. So I'm gonna just go and compare here. Comparing. Yeah? We need something with s squared on the denominator. So starting with denominator. Yeah. Now if you go and compare, so here you have number, right? Number. And I have here a number, right? So which rule is having, so here, which fraction is having a number up and s squared and a number down? So number and s squared, so here number, s squared and the number up. But if you go to the cosine, you get variable square, which is s and s squared and the number. So the good one is to go and compare with this one, yeah? So I'm comparing here. The right one is line number 4. So line 4, yeah? Line 4, so I'm just calling this line 1, line 2, line 3, line 4, line 5, 6, 7, and 8. Okay, so line number 4. Then comparing the denominator first, solution. So starting with s squared plus 25, which is the denominator first, equal to s squared plus b squared. then can you check for me what is p squared? Then p squared should be 25, and always you should go with p positive, right? P should be 5, yeah? Now going back to numerator. Now the numerator is supposed to be p. So in the rule, we have p up, b, yeah? But p is 5, right? Here it says you should have p up on the numerator, which is 5. But I have 6 here. But I can play with this and say, hey, if I have 6 over s squared plus 25, I need 5 here because I have p squared. Let me write it like this. I'm supposed to have 5 squared here, right? And I need 5 up. Then I will divide, so I will multiply this by 5 over 5, right? Yeah? Then I'm not changing anything because I'm multiplying by 1. Now taking this, which is this thing, outside. So when you go with Laplace inverse now, yeah, and you apply the linearity and taking this outside. So I'm taking this outside the Laplace inverse, then I will get 6 over 5, and then Laplace inverse of, now I have what I want, so s squared over 5 squared, right? Now this is b over s squared plus p squared, and it says this is supposed to be sine of, you don't replace the t, you replace the p, and you will get 5t, and then you are done. Done. Sorry, I forgot here the 6 over 5. 6 over 5, yeah? So 6 over 5, and then 6 over 5 sine 5t. More questions just to show you. So always I'm gonna have the same question, so I will I need more space here. So the question always asking for finding the f of t given f of s, right? So let me go with another question from the same page number. So here is question number 5. Question number 5, or we could go with question number 3 first. So let me go with question number 3, which is s plus 2. Question number 3, which is s plus 2, yeah, over s plus 2 over s squared plus 4s plus 20. Now I'm gonna tell you the story. If you have a fraction, always you're gonna have a fraction. If you have something simple, then you are done. If you don't have something simple, then you need to play with your denominator. Now my denominator is none of these. It says you have s squared, but you have 4s here, and you have 20. Here we have something extra, yeah, which is not good. In this case, you always look for either completing the square or partial fraction decomposition. I need you to go for partial fraction decomposition. I will explain this in details, but I'm going to tell you here what is the partial fraction decomposition. It says if you have p of x, p of s now, over q of s, then you look at the degree, say degree with degree of p equal m, and degree of q equal n. Number 1, if you get that m bigger than n, which means the degree of the numerator is bigger than the degree of the numerator or equal, then you go with long division. Number 2. So number 2, if m is less than n, then there is some cases. Let's say that n equal to, if n equal to, so here special case, when n equal to and q is irreducible. Irreducible means cannot be factorized. Yeah, cannot be factorized for some reason. B square, for example, if you have b square minus 4ac is less than 0, right? Then you cannot factorize this. Then this is just a special case, but I will do the general case later, but keep this in mind because I will go for a general case later. But we are in this case now where we have numerator degree here is 1, right? And the degree of denominator is 2. Then because the 1 is less than 2, then you will not do long division, right? Then you look at this one, can I factorize? If you cannot factorize this thing, then you need to do, in this case, you do completing the square. Completing the square. What is completing the square? I will tell you here. You add and subtract b over 2a, right? So this is the rule. This is completing the square. So you know what is, now let me write here. So I will write here in red, if you have as squared plus bs plus c, yeah? And then what is a? A is clear here. A is 1, b is 4, and c is 20, right? Now you need to add and subtract b, which is 4, over 2 times 1, yeah? And then square. Sorry, I forgot here, there is a square, yeah? There is a square here, yeah? Then square, yeah? Then you will get here plus minus 4, yeah? So you add and subtract to the denominator plus minus 4. So let me do the solution here, yeah? So we don't need that side here because we need a space, yeah? Just remember one more time, if you go here, you're gonna find always we have one s, right? But here you have two s's, right? For this reason, we need to look for partial fraction decomposition. Here is the solution. So I'm gonna just go for s squared plus 4s plus 20, which is the denominator here, and then I add and subtract that 4, right, which is minus b or b over 2a squared, right? Then I'm gonna have something like s squared plus 4s plus 16, right? Sorry, plus 4 plus 16, right? Now this is a, you call this completing the square, so this is a full square. So this thing will be just s plus 4 square, right? And plus 16. Now let me show you what we got now. We got that s, let me write here, s plus 2 divided by, now s plus 2 squared plus 16. I like to write the 16, this 16, as 4 squared. Plus 4 squared, right? And we need the Laplace for this thing. So we need the Laplace inverse of this guy, right? The Laplace inverse of this guy, right? How you do the Laplace inverse of this guy? Now we need to compare, right? So you are here and you are looking backward. So which one has an s up and s down with squaring here, with some shifting for s, right? Some shifting for s, and you have a number here squared. So if you look for denominator first, shifting s and squaring it and adding a number square. And then up you have s shifted. Now look here, so if you look here and there, here you in the sign you have up a number, but here you have an s, right? You have an s plus 2. But if you look at the cosine, then you have s shifted, and squared, and plus a number square. So this is a good one. So you need to compare this with line. So comparing with line, so line 8 in the table. Table 7, right? Now if you go and compare this thing with line 8, then you need first to start comparing. So I don't know what is this. Now comparing denominator, can you compare the denominator right away? Now it's clear that s plus 2 squared plus, so let me write it there. So s squared, s minus a over s minus a squared plus 4 squared should equal to whatever we have, s plus 2 and s plus 2 squared plus this is b squared and this is 4 squared, right? Now comparing first the denominator, can you see that a should be minus 2? Yeah? A should be minus 2 and b should be 4. Is that clear? Hopefully that this is clear. Then it says if you know a and b, then you are done, because you replace a with that a and you replace b with that b and you are done. Then the Laplace inverse of this is just e at, which is minus 2t, and then here cosine, right, and pt 4t. So you replace a and b and you are done. So here is your answer. Yeah. Now let's go with question number 5, just to show you all the cases, or almost all the cases. You have 1 over, so you have f of s equal to another one here, you have 1, and you have down s squared plus 4s plus 8, s squared plus 4s plus 8. Let me show you the difference when to use sine and when to use cosine. Now let me go back. So if you go and compare the degree equal 0, degree equal 2, right? Now in this case 0 is less than 2, then you need to go with partial fraction, yeah, partial fraction. But there is a special case. It says if this is irreducible, is this reducible or irreducible? It will be irreducible, cannot be factorized, For some reason it cannot be factorized, maybe because b squared minus 4ac is negative, right? Now in this case you need to complete the square. Again, if you go, so I'm gonna go, because the degree is 2 here, and irreducible, then I'm gonna add and subtract. So completing the square here, solution, completing the square for denominator. Again, you have to ask yourself why we don't apply the table right away, because here you have s square and s, you have two s's here, but all denominators here, they have one s. Yes, you can multiply this out, but it will be very difficult to compare later. Now the best thing is just to complete the square by adding and subtracting p over 2a squared. Yeah, comparing this, let me write here, if you write here as squared plus bs plus c, and you compare what is your a, what is your b, again you will have the following. So you will have plus minus 4. Yeah. Now let me go for that thing which is 1 over s squared plus 4s, right? And now you are adding 4 and you are subtracting 4, right? Yeah, adding 4 and subtracting 4, right? And that is the 8 that we already have, right? So I'm adding and subtracting 4, and I combine these things together, right? Together, will give me a 4, right? And this thing will give me, let me just tell you about that thing. It will be 1, and factorize this, you will get s plus 2 squared plus 4. And I like to write the 4 in a different way. I like to write it as b squared. So I like to write that 4 here, right? That 4, I like to write it as 2 squared, right? Now let me compare now with the table. It seems to me that this is almost the table, right? So let me compare. Which one to compare? You have a number and s shifted squared plus number squared. Number and number, number and number. So here number and number, right? So here is number and number, so line 7, right? Now comparing, if you go and compare here, s plus 2 squared plus 2 squared, denominator equal denominator, right? Equal to s plus a squared plus b squared, right? Now can you tell me what is a and what is b? Clear, a should be minus 2 and b should be 2. Good. So we have the b and we have the a. Now you can go back. If you have the b in the numerator, do we have here what we want? So here it says you're supposed to have 2. So where is the 2? Where is the 2? Now we don't have the 2. If we have the 2, then we are done, because we need b and b squared. Now let me multiply by 2. So this one, I can take it away and say it is 2 over 2, right? And now I need that 2, but that half I need it to be outside. Now going back, so I need the Laplace transform of this, which is now 2 over 2. I'm writing this 2 over 2, right? 2 over 2. Yeah? And here we have s plus 2 squared plus 2 squared, right? Yeah? And this is, let me write it as the 2 squared, right? 2 squared. Yeah? So we have the b squared, but we are inventing the b up. Now I don't need that fraction here, which is 1 over 2. I take it outside as 1 over 2, right? 1 over 2. And here is, sorry, Laplace inverse, right? Laplace inverse. And things are ready now. You have 2 over s plus 2 squared plus 2 squared, right? And now you have b squared, b, and you have s minus minus a, right? So then we're going to have e power, here the sign, at. A is minus 2t, and then is it sine or cosine? It is sine, and then 2t, and then we are done. So we did 2 things on completing the square, and now let me tell you what you will do if if you can factorize the denominator. So here is just, I was explaining to you, if you have P of S over Q of S, and you have degree here, degree is M, and this is degree is N, right? And we know that M is less than N, so you don't do the long division. Then what you're gonna do, and we have the special case we already said, if this is of degree 2 and it is irreducible, then you complete the square. Now what if it is degree 2 and it can be factorized, or if it is with degree more than 2? Now I'm gonna tell you there is some cases. Case I, it says if Q of S can be factorized as, say, S minus S1, S minus S2 up to S minus Sk power, no power. So you can factorize this to N, so we degree N, so N and N, so N linear factors, N linear factors with multiplicity 1, all with power 1, 1, 1, 1. All are different. All are different factors. You need to go to the calculus 2 and review this thing. Then you can write this as A over the first factor plus B over the second factor plus 0, 0, 0 plus the last. Let me just go and say this is A1, this is A2, and the last one is N over S minus Sn. Okay? Case 2, if any of say if this thing S minus SR has multiplicity, so one factor, one linear factor has K multiplicity. Yeah, when you factorize, for example, you get S minus 2 squared, so it is doubled. Then for this factor, you will have K, you will have K fractions, which are, if you like, you could say the first one is A1, yeah, over S minus SR power 1, yeah, and the second one is A2 over S minus SR power 2, and then plus 0, 0, 0 plus A K over S minus SR power K. This, by the way, these are the roots for the polynomial. Now, if you have something like S minus 2 power 2, then you will have the S minus 2 power 1 with a constant up in the numerator, and the second one will be S minus 2 squared and another constant up. Okay, there is one more case. I'm just reviewing this for you. Reviewing this very fast. If you have one more case, if you have, or two more cases, case number 3, if you have P over Q, if Q has one factor, one quadratic factor with multiplicity 1. 1. When I say multiplicity 1, I mean with power 1. Power 1. I mean power 1. Yeah? Then for this, say it is this. Say this is the factor. The factor is, say, the factor is ax squared plus b, sorry, it is s squared plus bs plus c, right? Then this factor, then it, then this factor will have one fraction. What is that fraction? It is like the following. It is as plus b divided by as squared plus bs plus c. Yeah? Just to tell you, here a and b are the variable. A and b are things to be calculated, right? But these a, b, and c are given. Yeah? Now, if you have this, and it is, say, the factor, is it, did I say q has one quadratic factor, which is irreducible. So I'm gonna add this, I forgot this, and this is irreducible factor. If it is irreducible, then it is square, then above it should be a linear, should be with power 1, right? 2 power 1, yeah? And when it is linear, then you have constant only. What if this is case 3, right? 1, 2, 3. And then case 4, I can go with case 4 now. If you go with case 4, if this thing, which is as squared plus bs plus c, has multiplicity k. So irreducible, so this is irreducible. Irreducible, and with multiplicity k, multiplicity power k, k. Yeah? If you have this, then what will be the fractions? Then this will have how many fractions? Will have k fractions. And you know the story, just to tell you what will be the fractions, just to tell you very fast. So here is the first fraction, so I'm going with case number 4, yeah? Case number 4, I'm gonna write them up here. Case number 4, so first you're gonna have, for example, a1 s plus b1 over here as squared plus bs plus c, and then you're gonna have a2 s plus b2 over as squared plus bs plus c squared, and then you continue like this till the last one, which is aks plus bk over this thing, which is as squared plus bs plus c power k. Good? So this is just to review something given to you in calculus 2. So power k, yeah? Let me solve more questions on this. One on this, at least one question. Let me solve question number 30 in the book. It says, you have now question 30. Yeah, here is question 30. Still asking the same thing. Now, but I'm giving you in a weird way. I'm giving you an equation for fs. I'm not giving you a ready fs, 2s plus 5, right? Over s squared plus 2s plus 1. Good? So I don't have an explicit formula. Look here. Here it says you can compare if you know f of s, but I don't know f of s. I'm giving you an equation for f of s. Before doing anything, you need here first solving for the solution. I will first know what is f of s to be able to compare. So if you, I'm solving for f of s. So solving for f of s, yeah, first, yeah. If I solve, I'm gonna just take f of s as a common factor. Then I left up here with s, and I left up here with -1. What I did, just multiply this out. So if you multiply this out, you get that thing. And then here we have 2s plus 5 divided by s squared plus 2s plus 1, right? Now I'm solving for f of s, right? How you gonna solve for f of s? You divide now, you divide everything by s minus 1, right? If you divide by s minus 1, what will you get? You will get 2s plus 5 divided by s squared plus 2s plus 1 multiplied by s minus 1, right? Yeah? Now I have f of s and I need to compare. So nothing here is given in this way. Nothing says you have s squared and you have 2s and you have s minus 1. In this way, I need to play with this f of s. Now I have here, let me just show you what is going on. What is the degree here? Degree is 1. Here the degree is 1 and 2, 3, right? This means I cannot do long division. Also, I cannot go with completing the square, because completing the square means if you don't have this, then you may think of completing the square. Now in this way, I need to factorize. So the first step for this is factorizing. So we have 2s plus 5 divided by s plus 1 squared and s minus 1. Yeah? Now let me go and do now partial fraction decomposition. So here we need partial fraction decomposition. So this thing will be, now let me go with this thing. This thing, because you have power 2, it will have 2 fractions, right? Because it is power 2, 1, 2. And this one has power 1, it will have 1 fraction. So plus and plus. This thing will have a up, and this will have b up, and here we have s plus 1, and here we have s plus 1 squared, right? So power 1, power 2, and then you go to s minus 1 and you put a constant here. Yeah? Now you need now to here having a common denominator. What is the common denominator? It is s plus 1 squared and s minus 1, right? And then here you need to multiply. When you have a common denominator, you have a times s plus 1 times s minus 1 plus b times s minus 1, right? Plus c times s plus 1 squared, right? Now this thing supposed to equal to 2s plus 5 divided by s plus 1 squared s minus 1, right? Now denominator, they are equal denominators, then numerators should be equal. So let me show you this. So let me show you this. Then we're gonna have, from this, we're gonna have 2s plus 5 should equal to a times s plus 1, s minus 1, plus b times s minus 1, and then plus c times s plus 1 squared. Now plug in values for s. If you plug in s equal, I choose from here, so I go for the roots for this. If you make this equal 0, you get s equal 1, right? So I start with s equal 1, then this side will give me 2 times 1 is 2 plus 5. So let me do it one time for you, and then equal to A, and then 1 plus 1, then 1 minus 1, and then plus B, 1 minus 1, right? And C, 1 plus 1 squared, right? Finally, this thing will be 0, this thing will be 0, this thing will be 7, right? 7 equal to 2C, right? And then from this, C equals 7 over 2. I got C. Now let me go with another S, which I'm gonna use S equal minus 1. And in this case, I'm gonna have minus 2 plus 5. I'm gonna get 3. And here I'm gonna get 0. And here I'm gonna get minus 2B. And here I'm gonna get 0. Yeah? And finally, B equal to minus 3 over 2. Now let me go with another S. I'm running out of any S that making all things are 0 or most of the things are 0. Then the easiest S that I can use is S equals 0. If you plug S equals 0 here, you get 5. And in this side, you get minus A. And in this one, you get minus B. And in that one, you get C, right? But here, you have your C here. And your B can be, you can put it here. You get 5 minus A, and minus B, you get plus 3 over 2, and C is just 7 over 2, right? Then you get 10 over 2, yeah? You get 10 over 2, is it? Minus 3 over 2, then you get 10 over 2, which is 5 with 5, then you get kind of A equals 0, yeah? The calculations are not that important, but you can go and review my calculations. So we have the A, B, and C, then ended up with the following. So A is 0, right? So kind of I'm getting A is 0, right? A is 0, right? And then here I'm getting my fraction, so we need the Laplace inverse of, we're supposed to have A over S minus 1, plus 1, right? Plus B over S plus 1 squared plus C over S minus 1, right? Now we know the A and B and C. So what is the A? The A is 0, the B is, where is the B? Minus 3 over 2, yeah? And the C is 7 over 2, right? Now I'm applying the linearity of Laplace inverse. It says this is 0, this is completely 0, yeah? Then I'm gonna have Laplace inverse of minus 3 over 2, and then down S plus 1 squared, right? And then plus Laplace inverse of 7 over 2, and then over S minus 1, right? Now this thing can go outside the Laplace inverse, and this one can go outside the Laplace inverse, right? And I left up with S plus 1 squared, S plus 1 squared. Okay, now here, so let me just go with 2 parts. I need to compare now 2 times to the table, right? 2 times to the table. So we have now table 7.1. So you need to compare the following. So this thing is nothing, it is minus 3 over 2. And I need an answer here, and this is 7 over 2, and I need an answer here, right? So what is here and what is there? Now from this table, we have 1 over S plus 1 squared. Now I need to compare with the table, so I need S1S down, it is power 1, and it is squared and shifted. So 1S down, shifted and squared. So this is line, using line I think line 6, right? Line 6. Now start comparing with the denominator. So s plus 1 squared should equal to s minus a power n plus 1, right? Then a should be minus 1 and n plus 1 equal 2, and then n should be 1, right? Now, one more thing here, one more thing. To be able to use this, I should have the n factorial. So let me calculate the n factorial now. N factorial equal 1 factorial equal 1. Should be up, should be in the numerator. And on numerator, on numerator. Yeah, should be on the numerator. Do we have this? Yes, we have it here, right? Now, if you want the Laplace inverse of this thing, which is 1 over s plus 1 squared, then this thing will be, you go backward now, you have everything, you have your a, you have the t power n, then you have e power minus 1t, yeah, and then t power, what is n? 1. Then you ended up with e and e power t times t. Now let me erase that thing now here, and then go with the second one. But the second one here is let me, line 6. Yeah, go with the second one, which is what is the Laplace inverse of so this guy goes here, right? I'm gonna just change the color for you. This guy is going here, right? And then the second one here, what is the Laplace inverse of 1 over s minus 1, right? Now comparing here, you're gonna discover that this can be calculated using line 2, right? Here. Now, if you compare this, 1 over s minus 1 should equal 1 over s minus a, then a should be 1, right? Then doing this, you will have e, then you can go back, you know your a now, it is 1, so you have 1t, then you have et, right? This guy here should go to that place, right? Yeah, should go here. And then you ended up with your solution, which is, here is the solution, the final solution. So final solution will be Laplace inverse of what? What was the question? It was, the question was 2s plus 5 over s square. Sorry, it is not like this. So what is the Laplace? So it was s, let me write it from here. It is s fs minus fs equal to 2s plus 5 over s squared plus 2s plus 1. Now it is asking me what is f of t, right? Yeah. Now I'm telling him f of t for this one should be minus 3 over 2. I think it was t e minus t, I'm not sure. And then plus 7 over 2, and then e power t. Yeah. And then we are done. Actually, I have a remark for you about this one. In all equations, all the differential equations that we're gonna solve, we're gonna have an equation in fs where you need to do some algebra and get your fs first. You get your fs first, and then you do Laplace inverse, yeah? Then you do Laplace inverse. This is what we did to get f of t, right? Yeah? And by this we reach the end of today's lecture. Thank you for listening, and see you next time.